Okay. Yeah, so last time, I just recap a little bit, especially because Matthias mentioned that some people weren't really sure why I was doing what I was doing. I occasionally mentioned all this in Poland a few years ago. I think Matthias was there halfway through the first lecture, one of the more senior members of the Polish physics induction study and said, why are you telling us all this? My reply was, well, you'd invited me. So, right. So, I was going to do a very simple-minded thing. Okay? So you're used, so from your quantum mechanics, or quantum field theory first course, you're used to the idea of computing scattering amplitudes. Okay? And usually, when you do this, you kind of only compute 2 to 2 because it all gets a bit too messy and harder to do higher scattering amplitudes. So we have some particles coming in, and we want to find the amplitude for the particles coming out. Okay? And you just know that if you're doing a standard interacting quantum field theory, then you'll just get more and more tired doing higher and higher diagrams, because if the particles coming in have enough energy, you'll be able to produce arbitrary numbers of particles coming out. Okay? So if you take just, for example, that phi-4 theory I started with, you can draw endless sort of nutty diagrams with 2 particles coming in, huge numbers of things coming out. And as long as there's enough energy in your 2 particles coming in to allow all the coming out particles to be on shell, okay, then there'll probably be a non-zero amplitude for that to happen. And of course that's what happens in real quantum field theories. If you fire particles fast enough at each other, say as I said at CERN, then you produce all these exciting messes that people spend their time trying to analyse. But of course one result of that is that if you think about, for example, the amplitudes for 2 incoming particles as functions of the ingoing momenta, okay, each time the incoming, the sort of total energy, what you like, the forward channel energy, okay, the total energy, becomes such that you can produce more particles in the out state, you'll expect something slightly funny to happen in the amplitude. Technically it's because there's this unitarity constraint, which means sort of the total probability to get something coming out is equal to 1. And each time there's some new possibilities, there's a new term in your amplitude unitarity equation. Okay? And you expect some sort of complicated piece of analytic structure even if you're just looking, say, at the 2 to 2 amplitude. Each time something new can happen, there'll be some sort of branch point or something complicated in the amplitude. Okay, so the analytic structure of amplitudes in general quantum field theory is extremely complicated. Right? And I was trying to think about the question about, could we perhaps have a theory where none of this mess happens? Okay, if we're going to hope to get an exact answer for the S matrix, then it seems extremely unlikely. So if we have an S matrix encoding all of that, then one single function would have to encode all of that complicated behavior, and that looks kind of hopeless. But if there was a particularly simple theory, such that this never happened, and the only thing that you ever got when you fire 2 particles at each other is 2 particles coming out, no matter how much energy in the incoming particles, that would give you, well, A, it would be quite kind of cute that would happen in a non-trivial theory. Of course, in a free theory, that's exactly what happens. But in an interacting theory, that's seems rather surprising. Okay. And B, you might think, having trouble with this, you might think that you would have some hope of finding then exactly what the S matrix is. Okay. Because at the moment we've only looked at 2 to 2, you then have to worry about 3 particles coming in and 3 going out and all the rest of it. Okay, but at least it would be interesting. Okay, so what I was trying to do yesterday was just look simply at tree level to see what constraints that implied for the simplest possible theory, which starts off with a phi to the 4 interaction. So we've got half phi squared, that's a half minus half n squared, phi squared minus lambda, and the 4 factorial phi to the 4th. We found on its own that's not enough, right? Because we found a constant for the 2 to 4. Okay, so on its own that's not enough. But because it was a constant, we were in this lucky situation where we were able to cancel it off with a phi 6 term, okay, for 2 to 4. Okay. But it was fairly clear that's not good, well, it's not completely clear, but I'll tell you that if you then look for 2 to 6, okay, again, that's not enough to cancel everything out, although it does leave you with just a constant with my slightly improved thing, so then we added on a phi to the 8th. And we believe that if we carry on that process sort of iteratively or recursively, we'd end up with a theory with no particle production to any number of outgoing particles. Okay? So you start off with 2 particles and always only get 2 coming out. Okay? And I claimed that that led to Extraordinary. And I showed you the first steps of the way. So the first 2 terms that we got there were consistent with the expansion of the Extraordinary Lagrangian. Okay, so that was kind of cute. So that was the sort of purpose of that, to show that there are these rather special properties, unexpected properties. Now, I'm just going to give you a teeny hint, because then we said, well, let's look at the... we were a little bit specialised here, because we start off with a phi 4 term. And if we're just looking in perturbation theory, you could equally well start with a phi cubed term. Okay, on its own, that looks a bit, phi squared plus phi cubed looks a bit weird, but if we're imagining later on we're going to add higher order terms, then we could maybe make something where the potential still looks sensible. So we wanted to start off with L is a half d phi squared minus a half m squared phi squared minus 1 over 3 factorial lambda phi cubed minus 1 over 4 factorial mu phi to the fourth. Okay, so we start off with this bit, and then I said let's see whether we can add on a sort of correction term to that to try and again cook up this no production property. And I said a hint as to how to fix, so it's not obvious that this would work at all, and if it does work, it's not obvious that it would fix the relationship between lambda and mu, but a little idea which is actually reminiscent of some of the ideas people in the higher dimensional amplitude scale do nowadays, is to think about killing off poles. Okay, so if you want a function to be zero, it certainly has no poles. And I told you, so I'm afraid time is now running this way, that if we start off with two actually sort of collinear particles with equal light cone, well actually static, equal light cone momenta, so m into 1, 1 and n into 1, 1, then that leaves us with actually one, if we have a 2 to 3 process, that leaves us with sort of 1 degree of freedom in the outgoing momenta. Okay, and I said, let's try setting the outgoing, one of the outgoing momenta to be m times 1 plus delta, and then beyond shall it be 1 over 1 plus delta. And then these ones will get fixed by overall momenta conservation. I don't tell you what the answers are, but A and B will be functions of the 3 momenta that I fixed. Okay? And then I said that in fact, at delta equals 0, so both internal propagators are on shell. Okay. Sort of geometrically looks sort of reasonable. We've got ourselves a sort of bunch of equal. And we'll talk probably next time a little bit about the structure of these on-shell diagrams in more generality, because it will be important to questions about bound states and this thing called the bootstrap, which is... Yep.
How to static particles with mass n can produce 3 particles? They all run out of energy.
Okay, so we're looking near... Okay, so this is going to happen at some complex place, okay, but we're looking at these things as a function of the rapidities. It's a good question, but yes, it's going to happen not at real momenta.
So it's an unphysical process.
So it's an unphysical process from that point of view, but the whole amplitude is going to be an analytic function of everything, okay? So if the whole amplitude for physical values of rapidities is going to be, so also of these guys, okay, we could cook up values of these guys where it would be, if the whole amplitude is going to be 0, then this thing would also, its continuation would also have to be 0. Okay, so it's sort of legit to consider. That's a good question, though, but yeah, that's the answer. Okay, so at this thing, this would have. It's a little bit like when you draw, you know, when you look at an ordinary, say 2 to 2 amplitude, it's got a pole there. Okay, but that's not happening. If all the particles involved are stable particles, that's not happening at a physical value of these momenta. Okay, but still, for this amplitude to be, you know, for this, let's say if these were different particles and we wanted this thing to be this amplitude to be 0, we'd have to have that pole cancelling as well. Okay, even at the unphysical. Okay, so in fact at delta equals 0, both of these internal propagators are on shell. So this diagram looks like, as a function just of delta, looks like 1 over delta squared. So the task that I said would be to find some other diagrams which would also be on shell and have a second order pole that could possibly cancel this, that you construct from a little toolkit consisting just of your lambda 3-point particle and your mu 4-point vertices. Okay? And to start with, it's kind of unclear that you can do this at all, so I was going to give you just one more little hint to show that these things are a bit curious, and that is that in fact the diagram, the first diagram you should look at, looks like this. Okay, so again the momenta are 1, 1, 1, 1, and A, so I'm setting n equals to 1 here just to explain, and this will be 1 plus delta. Okay, and naively, that hasn't got a hope to produce a double pole, so that's why you might get a bit stuck trying the exercise, because there's only a single internal propagator. But it's a sort of funny feature of kinematics when you've got collinear momenta, is that the orders of poles don't quite line up. So this propagator here, right, so for this propagator here, I've got, what have I got? I've got the momentum is equal to m times the conserved momentum, and we get 1 minus delta, that's 2 minus 1 over 1 plus delta, okay, conserving the left and right components. So p squared minus m squared is equal to m squared into, I've got 1 minus delta times 1 plus 2 delta over 1 plus delta minus 1. I think that's equal to 1 plus 2 delta. Okay, which is equal to n squared over 1 plus delta into 1 minus delta, 1 plus 2 delta minus 1 minus delta, which is 1 plus 2 delta minus 2 delta squared minus 1 minus delta, which is equal to, I should do this all on the board, the whole thing, so we get cancellations there, and there, there, and there, so the whole thing is equal to minus 2 delta squared times m squared divided by 1 plus delta. So 1 over p squared minus m squared, or let's say I over p squared minus m squared, minus I over 2 m squared, 1 plus delta over delta squared. Okay, so that diagram actually does give you a double pole in delta. Okay, so that's the sort of first step on the way to checking. So that diagram has a potential to cancel this diagram. Okay, so if you work out all the details, well, we'll find out there's one more twist, and there's one more slightly unexpected thing, but if you get everything right, then you get the right answer. Okay, good. So that was the first thing. And again, it's the same task, okay? And then the claim was that if you carried this process on, you would again generate one of these special Lagrangians, which has no particle production, okay, at least at tree level, and this would turn out to be this Bullard-Dodds gadget, which, roughly speaking, instead of having e to the phi plus e to the minus phi, that's this. Okay, so that doesn't have a phi to minus phi symmetry, but it turns out these exponential interactions still conspire to give you a theory with no particle production. Okay, and I just wanted to mention quickly that we can now expand the zoo. So I mentioned this in passing last time. So how to expand the zoo. So of course there are many integral models, many models which secretly have this property, okay, sigma models, all these sorts of things as well, where though for those models actually the nature of the quantum asymptotic states can be a little bit more hidden. Okay, even for the continuation of this top theory, when I take the coupling imaginary and I get my sine-Gordon theory instead, that has these non-perturbative soliton states we might talk about a little bit tomorrow. These ones, the ones I've shown you so far, say when the coupling is real, are particularly nice because you can see all the asymptotic states straight away with the Lagrangian. We can expand the zoo a teeny bit by looking at theories of coupled massive fields. Okay? So we'll consider a number, let's say R, of coupled massive scalar fields. So I could call them phi 1 up to phi r, okay, so before I had just one of them. And then I can write down the most general possible thing. I want everything to be massive, so I want my potential to look reasonable. I could write down L is a half, and the sum of d phi squared is 1 r. okay, minus a half, and then some sort of bunch of mass terms. So I could introduce a great big matrix m squared ij phi I phi j. Okay, so if we diagonalize that m squared, we'd have a bunch of masses in theory. And then we can start adding in interactions. So I'll start off with writing the most general possible set of 3-point interactions, C, I, J, K, phi I, phi j, phi k, plus and so on. Okay? So now we've got a much bigger playground of things to experiment with, but again, we'll try to find theories which have these slightly miraculous properties. Okay? So in a suitable basis, which would be us to find, we could take n squared to be a diagonal matrix of n1 squared to nr squared, which we'd associate with the sort of classical masses of the little excitations of the field. Okay? So we'd have a bunch of little classical excitations, a bunch of little fields, phi 1 up to phi r, once we've diagonalized that thing, which then talk to each other through this 3-point interaction, okay, and higher interactions. Okay? And the game would be, so which choices, so the question is which choices for N and C lead to what I'm going to call purely elastic scattering. By which I mean no production of particles, which is what we had before, but I'll actually have a new bit as well. I'll also say that it should be diagonal. So phi I always goes to phi I, not phi j. Okay, so in general you might imagine if I start off with, say, 2 particles of type 1, okay, I might end up with 2 particles again, but they might now be of type 2. For example, in the Sine-Gordon theory, when you look at the scattering of kinks in quantum theory, something like that happens. So if you start off with a kink and an anti-kink, well, actually, you still have a kink and an anti-kink, but they're all might get swapped around. I want none of that, okay, so I want everything to be diagonal. So these would be the simplest possible multi-particle quantum field theories I can think of which are interacting. Okay, and that second constraint is kind of a new constraint compared to my initial theories, because the initial theory says there's only one sort of particle anyway. So this is an easy drawing. Any questions? We'll see. Oh, okay. Good, so that's definitely harder. There's more freedom. I think there's maybe a paper where someone tried to look at it for 2 components. But I think I know what the final answer is going to be, or at least I know a big set of examples. Okay, so lots of calculation. I think it might be interesting to understand. But the final answer will at least include L is half the phi squared minus a function I'll call v of phi, and v, nasty feeling I've got this thing all upside down. So here we start to see a hint that even in these simple cases we can generate or find an excuse to look at nice structures involving Lie algebras and so on. V of phi is going to be m squared over beta squared, convenient constants, times the sum from 0 up to r, okay, of some little constant na e to the beta times alpha a dotted with phi. So phi is going to be a vector phi 1 up to phi r, okay. Alpha 0 up to alpha r is a bunch of r plus 1 vectors in r to the r, okay, which I'm going to have to specify in a second. Okay, question? Okay. Okay, so here's a natural generalization of the two gadgets I've got on the top of the other board. Okay, so now I've got these fields which point, all of them, so phi are all little vectors. Okay, my field lives in r to the r, an r-dimensional space. And I construct a bunch of exponential interactions. So if I was in just one component again, okay, and I took my alphas to be plus and just plus, the vectors were plus 1 and minus 1, I'd be back to the top guy I've got at the top of the board. Okay? If I'm in higher dimensions, I can kind of make these vectors point in more complicated different directions, and I've got a whole class of exponential interactions. But if I expand that thing out, okay, as I did expanding those things out to get my first few perturbative terms, I get that n squared, my mass matrix ij, would be m squared times the sum from 0 up to r of na alpha a I alpha a j, if you think about it, and Cij k would be m squared times beta times the sum from 0 up to r. So that's a is 0 up to r again, a is 0 up to r of na alpha a I alpha a j alpha a k. Okay, and so on. Okay, and I'll arrange these NAs are such that the sum from 0 up to r of NA alpha A is equal to 0. Okay, that kind of makes the vacuum, that's the minimum of V, at phi equals 0. Okay, right. So the question is, okay, so that's a sort of possible set of things we could try. What are the sets of alphas? What are the sets of r plus 1 alphas? Such that all these nasty production amplitudes cancel. Question, yes?
Why r plus 1 times means alpha?
Okay, so let's think about the simplest case in one dimension. Okay, so if I just chose 1, okay, so 1, r is equal to 1. Okay, so if I just chose to have one vector, then my potential at the top would look like e to the phi or e to the minus phi. Okay, that would be actually what's called the Liouville theory. It's massless. So the potential for that case, if I just take one component here, okay, so I take e to the phi, that's giving me a sort of potential that looks like that. Okay, and in some sense the vacuum sitting off at minus infinity, and it's flat there. It's a way of understanding why the Liouville theory is conformal. Okay, it's a bit like there's no zero, there's no minimum to that thing about which there's a nice sort of phi squared term. Okay, if you go to high dimensions, if you start off with just r of these things, so if I went from 1 to r rather than 0 to r, there'd always be a direction I could go such that all of these exponentials was decreasing. Okay, so there'd be a sort of place where it would go off to minus infinity. But if I put an extra one in, it sort of, if you think about the two-dimensional case, I've got two directions going up like this. At the moment, my field can sort of slide off sort of behind my back. So I put in a third one, and I put another wall in, and now I've confined everything, and the thing is massive. Okay, it's to do with my wish to have a theory of massive particles. Okay, but that's a good hint, because you see, if I did take 1 to r instead, then I'd be in these classes what are called non-affine polar theories, which are the theories that people look at as generalizations of the Liouville model. Okay, and they have many interesting properties, but they're non-rational conformal field theories in general. Okay, and what we're considering here is in some sense the generalization of the idea that starting with the Liouville theory you can perturb it and generate the Sine-Jordan theory, or the Sine-Jordan theory. Okay, and you can think about this as being obtained by adding from the sum from 1 up to r, which is a conformal field theory, an extra term, an extra interaction term, which is the a equals 0 term, which then turns it into a massive theory. Okay, but I'm a bit ahead of myself there because I haven't told you anything about what these numbers are. So in fact, the sets of good numbers are encoded in the affine linking diagrams. Okay, and for these cases you can construct a lax parents on improving classical integrability. So here's a little picture that I prepared earlier of what those linking diagrams look like. So this would be the zoo of what are called classical affine tonal field theories. And it turns out that for every affine Dinkin diagram, so these Dinkin diagrams, well, I think everyone's seen a Dinkin diagram, so they basically encode, if you think about it, there's a sort of rotational symmetry of everything. So all that we care about in these models is the relative geometrical configuration and lengths of these r+1 vectors, okay, alpha 0 up to alpha r. Okay, we could rotate them around. And that's precisely what Dinkin diagrams encode. So the possible geometrical configuration of these r+1 vectors, which I know for sure lead to theories with these miraculous no particle production properties, are exactly encoded in the ADE diagrams, and then these slightly more complicated. So the ADE diagrams, all of these alpha r's have exactly the same length, right? And if you lop off one of the nodes, a suitable node, you end up with one of the non-affine Dinkin diagrams. Okay? And then these other ones are sort of little decorations, and in fact they come in two classes, a twisted and the untwisted diagram. And that's the set, okay? So the claim is that for all of these, a good classical theory emerges, okay, with the same miraculous properties of these two models I showed you before. There's actually some interesting twists in this, which I probably won't have time to tell you about, which is that for the case of the simply laced diagrams, and in fact this A2N2 diagram as well, they have a rather special property, which is that when you swap the long and the short roots round, okay, these non-affine diagrams, the little arrow is a sign that the diagrams these alphas are known as roots. Okay, so again, you probably all know. And the arrows point from longer roots to shorter roots. Okay? So for the ones where there are no arrows, that means all the roots are of the same length. For the other ones, that's no longer the case. And you can have a little operation which is where you swap, basically you send alpha to 2 over alpha squared alpha. Okay, and that sort of implements a swapping of long and short roots. If you want to sound extremely posh and fancy, you can call it Langland's duality. I think Langland's might not be so happy. But anyway, that's what you could do. And then you find that these diagrams naturally pair off. Yes, question?
So, could you say again what's the transformation of alpha?
Alpha goes to, so if we normalise all the roots to have length squared 2, if I send alpha to 2 over alpha squared times alpha, okay, then all the roots of length 2 just stay the same, and the ones of length bigger than 2 become length less than 2 and vice versa. Okay, and obviously the overall normalisation of everything doesn't really matter, but this achieves that swap. So then what will happen is, you see, we swap. So basically you just then flip the arrows. And then for all of the diagrams with arrows, apart from this one, this guy will actually go to itself again, because it's got both longer and shorter roots. Okay, all the others get paired off, so you get this sort of neat little manoeuvre. And it turns out, I mentioned very briefly, that in the case, say, of the sine-Gordon theory, if I put in a coupling, a beta here, okay, that's the sine-Gordon model. The sine-Gordon model has one of these famous dualities. It's what's called a strong, if you look at the full quantum theory of the sine-Gordon model, it turns out that if you take beta to 1 over beta, in suitable normalizations, it's probably not quite that one, but anyway, in suitable normalizations, basically beta to 1 over beta, the S matrix, which we haven't talked about yet, but the full quantum theory actually goes into itself. Okay? There's a sort of self-duality of these theories. It's a strong, weak coupling duality, but between a single theory. Okay? The S matrix goes to itself. And you have to think about, well, what's going to be the generalization of that properties for these more complicated theories. And it's kind of natural to think that we should worry a little bit about the length of the roots as well. Okay? So it turns out that in fact the generalization, not only do you send the beta to 1 over beta, but you also have to do this little flip of the root system. So then these diagrams, the A, D, E, E, the A, Ds and E's, and this A to N2 one, go to themselves. Okay? And that actually results in the quantum field theory being rather simple. Whereas for these other cases, they pair off. Okay. And that was the source of a lot of trouble when people were first looking at these things. Because to start with, they couldn't really figure out, in fact, people didn't guess that this is what was going to be going on. Okay. But they looked naively at quantum. We found a bunch of classical theories which seem to have this nice scattering property. Okay. But when you try to compute the quantum theories, you can do some very simple tests. For example, now we have a theory with more than one sort of particle. Right? And so now it's a finite task to compute this M squared matrix in your, you take any basis you like for your Lie algebra, so you find some representation of these affine roots, alpha 0 up to alpha r, okay? Just pick some basis, look up in your favourite textbook about root systems to find out a way of representing these vectors with these sets of dot products in the appropriate way. You then just compute by hand what this M squared matrix is and diagonalize it to find a set of masses. Okay, these you might call them classical masses in these theories. Okay. But then, of course, you have to worry, because it's quantum theory, you have to worry about how those masses might renormalize. So you have to start worrying about calculating, we've got a bunch of three-point couplings, calculating how the masses will shift. Okay, if you normal order everything, it becomes a finite. Okay, all the infinities go away, but there's still finite renormalization to be done. And if you do that, you find the first hint of this structure I've shown here is that for the cases of the A, D, E, and A2, N2 diagrams, the ratios of these masses do not change when you do this renormalization. Okay, at least to one group, that's as much as people have checked. But when you start doing it for these other ones, which flip over in pairs, you find the ratios of these masses, once you do this one loop renormalization, do change. And that was kind of upsetting, and people couldn't quite figure out how to construct guesses for S matrices which had such a property. But from the point of view of this duality, it's rather natural, because if you compute the classical sets of masses on both sides of those little double-headed arrows, you find you get different values. Okay, so as you go from weak to strong coupling, the mass ratios had better change, because they're heading off towards, their weak coupling limit in the dual theory is a different set of numbers from the weak coupling limit in the theory you first thought of. Okay, so there has to be something going on, and that's exactly what is going on. Okay, so there's kind of a lot of amusing stuff, and the full structure of that hasn't completely been understood. I should mention one other little fact, which is quite curious, is that at least for the classical masses, so they turn out so I'll mention this now, because if I get time, it'll rear its head again tomorrow, to be the components of an eigenvector of the corresponding non-affine Cartan matrix. So it's easiest to describe for the simply laced cases. If I take any of those simply laced diagrams and I delete the appropriate sort of the bonus node, okay, so for the A's it would be anything, for the D's if I delete one of the nodes on the fork, or for the E's, well, it depends on which one of the sort of a suitable extremal node, I'll get the Dynkin diagram of the corresponding non-affine Lie algebra. Okay, I can compute its Cartan matrix, and then rather than diagonalize that, I just think about what's in fact what's called the Perrin-Frobenius, the largest eigenvector of that matrix. Okay, and that has a bunch of components. It has R components, and those components are exactly the same with these numbers here, which emerged from looking at this object constructed from the affine Dynkin diagram. And it took people actually quite a while to figure out why that should be true. So that's now sort of, you can do it case by case, but mathematically it's rather odd, because the Dynkin diagram and the affine Dynkin diagram are just not the same. Okay, they're rather different structures. And in fact, you have to use some rather nice pieces of work done by Costant back in the 1950s to prove that. There was an observation by a chap called Mike Freeman a while ago of how that went. And I might give a hint about the mathematical structure that's behind that next time if I get time. Okay, so there's lots of sort of nice and slightly more advanced mathematics hiding behind the scenes of these relatively simple-minded calculations. Okay, good. So I've now had about half an hour. So let's see what I'm going to say next. Oh yes, I did want to say one more thing on this topic. So we've been worrying away about getting rid of particle production, but I'll just mention again what was a brief answer to Kostia's question yesterday. So the first lesson is that in 1 + 1 dimension there seem to be these interacting quantum field theories where there's no particle production, even though they're interacting. That's curious. Okay, so in particular, 2 to 4 vanished. Okay, so there's no particle. But what question, what about 3 to 3? Okay, so I'm always talking about the connected amplitudes here. So for 3 to 3, there'd still be some sort of residual bit from disconnected diagrams. But does this mean, does what we've just done, does this mean that the connected 3 to 3 amplitude is 0? Okay. And naively the answer is yes, because you just, every time we had one of these 0 diagrams for a 2 to 4 process, we just cross it and get a 0 diagram for the 3 to 3 process. Okay, so naively yes. In fact, no, not quite. Okay, it's almost 0, but not quite. And the reason is we ignored these I epsilon factors in. Okay, so the propagators look like 1 over p squared minus m squared plus I epsilon. Right? And so long as, for the processes you're thinking about, p squared minus m squared is not 0, then this I epsilon kind of doesn't matter. Okay, so it is okay so long as p squared minus m squared is not 0. Okay, and that was true when I was looking at 2 to 4 processes. But when I'm looking at 3 to 3 processes, then my type A diagrams can cause me trouble. So, this isn't true of type A, that was something like that, diagrams for 3 to 3. Okay, so if I have, let's draw it the other way around, because it'll be the same as what I drew before. A, B, C, D, E, F. Okay, so this line here, okay, this is on shell if A equals D or B equals D. Okay, you conserve momentum, so if, say if B is equal to D, then this internal momentum is equal to A, and everything kind of lines up, and it's also on shell. That's kind of obvious. Okay. And when you add all the diagrams up, okay, we'll also have diagrams with sort of different orders, and kind of the dependence on everything gets a little bit fiddly. We'll find a term that looks like some constant over x plus I epsilon minus some constant over x minus I epsilon. Okay, where x would be the deviation of, say, B from D or A from D. Okay, depending on where you are in the vulnerability space. Okay. And then you have this famous little result that the limit as epsilon tends to 0 of A over x plus I epsilon minus A over x minus I epsilon is something like 2 pi I A times delta of x. Okay? So you find that this whole amplitude, once you've added everything up, okay, vanishes apart from on this sort of subspace. Okay, this one-dimensional subspace, which only kicks in when this outgoing momentum is equal to one of the incoming momentum. Okay, and if you sort of conserve overall momentum as well, that turns out to be that this, as a set, the outgoing momentum has to be equal to the set of incoming momentum. 0 unless A, B, C, the set, is equal to D, E, F. Okay? So, what do we have? We have property A, 2 to 4 is equal to 0, no production. And now a new property, property B, which is that 3 to 3 is equal to 0 unless initial momenta as a set is equal to final momenta. Okay? So in general, right, say if you've got a 2 to 2 process, when you conserve momentum in 1 plus 1 dimensions, then the outgoing momenta are sort of fixed up to some perhaps discrete ambiguity. But when you go to 3 to 3 or 4 to 4 or whatever, you've still got freedom because you've only got one overall momentum constraint, okay, to vary those outgoing momenta. And that corresponds to the idea that when you have more and more particles contributing, they can kind of get together and create some new complicated stuff that you wouldn't see if you just looked at the 2 to 2 or 3 to 3 collisions on their own. Okay? So this is more generally 2 to n, and this would be in general the n to n amplitude has this property. Okay? So in these sorts of theories, the scattering is non-trivial, but only just. Okay, so it turns out scattering is still non-trivial. You can work out things like phase delays and find out that two particles do actually talk to each other, but they talk to each other in a kind of minimal fashion. And furthermore, it turns out that all this remains true in the quantum field theory. So the question is, why? So now I want to talk a little bit about that. So now we're going to start looking at this in a slightly more general way to try and understand these sorts of properties more systematically in a way that applies to the quantum theory as well. Are there any questions so far? Yes?
Is it essential for integrability that the flavors do not change? As you said, at 500 to 500?
So the answer is no. So there are examples, there are plenty of examples where, so there are examples where there are sort of internal, if you like, colour indices, okay, which can change in scattering. It is, I believe, essential that the masses remain unchanged in scattering. Okay? Because otherwise somehow the analytic structure won't be nearly so nice. Okay, so if you change the masses, then the outgoing momentum as function of the incoming momentum will be a bit of a disaster. Okay, so all the examples I know, the masses remain unchanged. But you can have examples, not these toner theories, but more complicated examples, where there are little multiplets of particles with the same sharing the same mass, which have this little internal colour label, which then does get shuffled around. Okay. In fact, that's quite crucial. So a lot of the interesting structure, for example, well, we'll talk about this later with any luck. There's something called the Yang-Baxter equation, which constrains scattering amplitudes. And that's only non-trivial when there's some shuffling around of internal labels. That gives you a matrix structure. It's relating to an idea. This sort of emerges when a theory has some non-local charging, conserved charges, which are not conserved in scattering. But we may talk about that a bit more systematically later. Okay, anyway. Any other questions? So, let me try and systematise it. That was a rather long introduction, I'm afraid. And I think I'm going to skip some stuff, at least by the time I get to tomorrow. So I can talk about more non-trivial things. But,
excuse me.
Yeah.
Does it mean that you break crossings in?
Well, sort of yes and no. It's okay. I mean, you know, in some sense, no, because we've also got this overall momentum constraint, so things just can't be on shells. I think in some sense, and it's just these delta function regions. So I think it's not inconsistent with crossing symmetry, right? Because you have this, you know, so your two. There's no way of going from 2 to 4, preserving individual. That's kind of I don't quite know how to express it better, but you know, you can't conserve individual momentum while you're doing that. So things can't all be on shell in the same way. So I think there are just these sort of sub-manifolds in your space. So you know, in some sense, crossing symmetry is preserved with something which is just zero everywhere. Okay, but then there are these, and as I mentioned briefly last time, some of these analytic S-matrix people in the 70s did kind of understand this process properly, okay, why this happens. So it's not just a feature of integrability. Okay, a number of these strange features of integral models turned out to have what was sometimes called prosaic origins in ordinary field theory. And this is one of them. So in a general scattering theory, you'd expect to have extra singularities and sort of funny bits with delta function support occurring when incoming and outgoing momentum are equal, for example. But normally you'd have this background, which would be crossing symmetric, behind it, which is non-zero. And the special feature of integrability is that background vanishes. Okay, so you don't get anything else at all. Normally, of course, you just ignore these exceptional traces. But in principle, you shouldn't worry about them. Okay, so that's section 2. So conserve quantities and factorize ability. Okay, so far we've got these sort of odd properties, but we're still a long way. I mean, our real goal is to find out these S matrices exactly. Okay, to find out the full S matrix. So starting off with n particles, we now know you only get n particles coming out. But we'd like to know, as a function of the incoming rapidities, what these amplitudes are. Okay, and then we can go away and do these much more fancy calculations with some A transats and all the rest of it to try and compute further properties of the model. But the starting point ought to be to just find these S matrices. Okay. So we had these two key properties, which was A, the particle production, and B, quality of initial and final momenta. And we saw rather laboriously how this seems to at least have signs of emerging just from perturbation theory, so it's not, as I say, it's not a miracle, but we still like to understand better how it works. Is it a coincidence? Is it kind of too much of a surprise? Well, there's another calculation I didn't show you, which we could have also have done at a classical level for this Sine-Gordon and Buller-Doppler problem, which is work out by hand symmetric conservation laws. Okay, so it's rather a cute little calculation you can do to try and find the existence of these extra conservation laws, and that's what I told you that Buller and Dott had looked at. And if you do those same calculations and you don't make a mistake as was initially made, then you find you land on exactly the same pair of theories as we've landed on here. Okay, so is that a coincidence? And the answer is no. So let's set up a sort of framework for handling. So what I'm going to do basically is I'm going to assume that we do have conservation laws, okay, and they do persist in the quantum theory, and then try and extract consequences from that. And the two consequences are going to turn out to be these two, plus a bonus one, which is that actually calculating the 2 to 2 S matrix is enough to compute the entire S matrix. There's a property known as factorizability of the 2 to 2 S matrix. Okay, so that makes the whole task of computing S matrix boil down to just computing one bunch of functions for 2 to 2 scattering. And that's why this whole field kind of works, why you can make progress. So we need to set up some notations, and I'll do all this slightly more generally before. I guess we've got about 15 minutes or something.
Well, we started with delay of 7 minutes, so we can get 7 minutes.
Okay.
With respect to 12 travels.
Pardon?
With respect to 12 travels, so you can...
Okay, good, so that's about 50, almost 50.
Yeah.
I'll just, whenever you want, I'll stop and we'll carry on tomorrow. So asymptotic states. And what do I really mean by the S matrix, okay, in quantum theory? So I'll look at things rather generally. So let's suppose, a little bit like these clever Toda theories, I have a theory with masses, let's say NA, NB and so on, and then for something to be on shell, I need that P bar A is equal to NA squared. Okay? And it turns out, so previously I talked about solving that by writing PA as M times A and P bar A, the underlying co-component, as M over A. Turns out it's slightly nicer to solve the constraint by introducing a rapidity, so another variable. So we'll solve the constraint and we'll parameterize the mass shell by writing the left component as MA e to the theta A and the right component as MA e to the minus theta A. Okay, there are all sorts of reasons why that's a nice thing to do in terms of the analytic structure that the S matrix ultimately has. But for the moment, it's just another way to solve the constraint. So theta A is called the rapidity. Okay? And letting theta A just go over all possible real numbers gives you sort of particles moving forward, and now to cross it, okay, so to take PA, remember crossing, say, was taking C to minus C, I'd have to take this to minus itself, so I'd have to replace theta A by sort of I pi plus or minus theta A. Turns out to be the right way of doing crossing. Okay, so that's a little bit different from before. So theta A is called the rapidity. Okay, so the analytic structure is much nicer. Okay, so the forward component of the mass shell then the forward component of mass shell has e to theta A positive, i.e. real theta A, and it turns out that the correct continuation to get the backwards component is this is on the line imaginary part theta A equals I pi. Okay. In fact, if you're more careful about it, crossing becomes sending theta A to I pi minus theta A. But we'll worry about that later. Okay. So now we can write an n-particle state. We'll write an n-particle state as, I'll use some symbols for this. So A1, A1 of theta 1, A2 of theta 2, up to AN of theta n. And I'll put a little in or out subscript. And what does that mean? Well, AI of theta A means a particle of type AI travelling with rapidity theta I. Okay? And if it's in, kind of visibly you think that all the particles are sort of moving towards each other, so as I go further into the path they just get further apart, so all their interacting is going to happen in their futures. And if it's out, it means they've all done all their interacting, they're now moving on diverging trajectories and all the interactions are in their pasts. Okay. Right. Now there's a little trick in discussing this, which is that this notation already slightly implied this. We'll consider smearing out the rapidities, so rather than go exactly on rapidity eigenstates, we'll smear the rapidities a little bit so we can start talking about wave packets. Okay, and this can be made precise, and people like Park have written papers showing how to make this more precise, but we'll just keep it approximate for now. So we'll smear the rapidities a teeny bit so we can consider wave packets. So we'll smear so we can talk about localized wave packets. Okay. And if we're dealing with massive theories, which I'll assume, we'll assume the theory is massive, no massless excitations at all. So interactions are short range. So that means once we've smeared things out, so we can say where each particle roughly is, then so long as they're well separated, the individual wave packets propagate like free particles. Okay, they just move along. They're asymptotic states, they just move along like free massive particles, until their respective wave packets overlap. And then something will happen that we can't quite control while they're interacting, but then later on the wave packets will separate again, and they'll again propagate like free particles. Okay, so we can localize the bits that we don't yet understand. So a state evolves as a bunch, technical term, a bunch of free particles, except at those moments when two or more wave packets overlap. Okay, now you have to be kind of careful with all of this discussion, because you know that in general wave packets tend to spread out over time. You have to do a slightly careful analysis to decide that you can start off with wave packets far enough apart that they won't have spread out too far until after all the interactions happen. But it turns out all that does work, so you can dot the i's and cross the t's on all of this lot. Okay? And then an in state, in this sort of picture, corresponds to a state which has no interactions as t goes to minus infinity. So that will be when all my wave packets are arranged in one particular order, and an out state will be the other way around. So I think I'll just write this bit down, and then we'll carry on with the rest next time. Okay, so an in state has no interactions as t goes to minus infinity, or there are more interactions, depending on which way around we're viewing time. So that means that the fastest particle lies on the left and slowest on the right in this sort of smeared picture. Okay, so let me draw it. So I've got one wave packet here, of course. Here I'm drawing it as if it's just a single field, when it's not really. These wave packets are pointing possibly in different directions, but it's roughly the idea. So I've got my particle with rapidity θ1, and that's the fastest of all. And then I've got a particle with rapidity θ2, travelling a bit slower. And then θ3, travelling even slower. And so on. So if I have a movie, right, and I imagine then running time backwards, okay, towards minus infinity, these guys will just get further and further apart. And conversely, if I run time forward, these guys will start bumping into each other, interactions will start to happen, and that's a bit that I don't yet know about. Okay, so that's a bit that we're going to have to find as an interacting theory, but at least while the particles remain separate, they just go about their business without worrying. So θ1, largely θ2, largely θ3. So, okay. This is a little bit reminiscent of what Jean Sebastian was talking about when he was talking about beta ansatz and why it all worked so nicely in one dimension of space, and it's a bit of a disaster if you try and do it in higher dimensions, because we've got this sort of nice relationship between the order of the particles and whether they're going to interact or not, and their position in space, and you can kind of visualize it in higher dimensions. That doesn't really work. Okay, so an out state, there's sort of nothing interesting in its future rather than its past. Okay, so the fastest is on the right, etc. So now I've got θ1 and then a bigger rapidity with θ2 and an even bigger rapidity with θ3. And so on, so θ1 less than θ2, less than θ3. Okay? And the whole task now is to get from this situation, where there's nothing more to know as we run our clock backwards in time, okay, through this messy period where everything is interacting, into this situation where there's nothing further going to happen, nothing more to calculate for what's going to happen in the future. Okay, the non-trivial stuff is going to happen in between, and that's what we've got to calculate. Okay, so next time, the first thing I want to do is just set up, there's a nice notation for all of this, which is due to Zamolodchikov, where we sort of avoid having to say these in and out labels. Okay, because if we start to give some significance to the order of these symbols along the line, we can kind of encode whether something is in an in or an out state just by the order of those symbols with respect to the rapidities of the features that are inside them. Okay? And that's sometimes called the Zamolodchikov-Fadeev algebra. Okay? And then the S matrix is going to turn out to be just a little rule for passing one symbol past the other. And then you can reduce all your S matrix calculations to just little rules about shuffling these things around. And the whole thing is encoded in some sort of basically a quadratic algebra known as the Zamolodchikov-Fadeev algebra. Okay, so I'll talk briefly about that and then how it's a quite efficient calculational tool for deriving the various constraints. And then talk a little bit about the properties, how we can use conservation laws to restrict what the possible options are for the out state for a given in state. Because of course, whatever the values these conservation laws have on the in state, they have to be the same as the values they have on the out state. That's going to restrict what could happen. So I think that's probably my time up for today.